room. I have in the room also two of my colleagues who are working with the particle work. So if there is any question on that, they will help me with the questions, answer to those questions. And I have also Andreas if there is any other question on the design process as well. So we are full team here, 4 persons in the meeting room. If there is any question, I will refer to them.
Thank you, Shafiq. Okay, so we will start again this with the next speaker, next presentation. So as you can see, our next speaker will not be here today. He was supposed to join us in Nice, but has a very important issue, last minute issue, and the Polestar e-motor teams has to cancel their trip, unfortunately. So as an alternative, we decided to do it as an online presentation. So our next speaker is Shafiq Natek from Polestar. So at PowerSys, we know Shafiq for quite a long time, since his PhD, I think, actually, in KTH. And since that, we tried to support him with all his very challenging projects while he was working in different companies, such as Rolls-Royce, ABB, Volvo Cars, and no Polestars. So yes, long story. I think we have achieved quite good things together. So Shafiq will present what he's working on right now at Polestar. So I think you can start, Shafiq. Shafiq, we can hear you very well normally.
Hello, everyone. And I would like to first apologize that I couldn't make it physically in Nice. Last week, I needed to cancel my trip because of the task force that we have internally, both myself and also my other colleague, Andreas Carlson, that we had planned to join you, needed to cancel our trip. Sorry for that. So let's at least make it virtually good. So, and I hope I can convey our message basically to you in the right way. Even virtually is not the best way always. I'm going to talk a little bit about the design and control of electrical machines, basically the Polestar way, the process that now we are following in Polestar. It includes electromagnetic, thermal, a little bit of mechanical, and also control simulations. As Corentin mentioned, I started using JMAG from the time I was PhD student in 2009, and I have been continuously using. These days, I still use it, but also I do a lot of support role in the company as well, in the previous places that I worked as well. So it's more like a combination of using and supporting other people. That's why I'm not anymore expert on everything, to be honest. So we have 2 or 3 of my colleagues. 2 of them are Gabriele and Michelangelo. They use a lot the particle works, another product being distributed by PowerSys on thermal simulation. I have also my colleague Andreas Carlson. So if there is any question I cannot answer, I will refer to them. About the content of the presentation, I will start with a small introduction about Polestar, our company, what we are doing. And then I will go to our current and future Polestar vehicles. I would like you to know how variant we have, how many variants of the vehicle we are dealing with, and how we are able to manage this number of variants in terms of the design processes, basically. So that is the reason that I'm showing you a little bit of like our vehicle portfolio. After that, I will go through our e-machine design process. I will show you how we do the design. It's more or less the same as what I presented last year, basically, on the design process. But we have an add-on to it, especially on the control and the cooling system design, which are basically the topics after the talking about the design process. At the end, I and my colleague will be happy to answer your question if there is any question. Hopefully, I can make it very clear during my presentation. About Polestar, we are an electric performance car company, basically. We are a spin-off from Volvo, and still we are owned by Volvo Cars, almost 50%, and also big part by the Geely Group, which is owning 100% of, or big part of the Volvo. So we have a big heritage from Volvo cars, of course, but we have also our own way of thinking when it comes to the design of the components, including electrical machine. And one very important target that we have is to not make compromise, basically, in our design process when it comes to different vehicles. So each vehicle we are looking at, we consider it as a unique vehicle, and we try to have a customized design basically for that vehicle that results in no compromise kind of in attributes of that specific vehicle. So that basically enforces a lot of requirements that we have on our tools and design processes. Now I'm actually presenting from our headquarter office in Gothenburg in Sweden. We have also another R&D office in Coventry in UK as well, which focuses more on the car body. We have production basically in China and South Carolina in US. On our vehicles, we started with Polestar 1, which was a hybrid vehicle. We are not producing that anymore because we are moving to full electric brand, basically. This was a nice, beautiful car, quite high performance, as you can see from the numbers here, both in combustion engine and also in 2 rear electric motors that we have. Our most sold vehicle and the product that we are selling today is Polestar 2. It comes in 3 basically different variants of a standard range, long range, single motor, and also all-wheel drive, where it is powered by 2 different basically motors. And for now, we are reaching quite good acceleration numbers for 0 to 100. With all-wheel drive, we can reach almost 4.7 seconds, and we are going to improve that in our next vehicle. You will see in the next slide. So something about future. Our next car is Polestar 3. It's a huge SUV, beautiful car. And this is gonna be announced in a couple of weeks, basically, and it will be, you will see it on the road from basically next year. Our signature car will come to the market in 2024, 2025. It's called Polestar Precept. It's a beautiful sedan, quite big one as well. And you will hear later on its impressive like performances 0 to 100 with not so many seconds, I can say. I cannot really release at this point our acceleration, but it's gonna be impressive and it's gonna be far better than Polestar 2. And this is another vehicle that we have, is a Roadster. So the reason that I showed you these variants, so we are not selling today so many cars, and in 2024, 2025, we are still going to produce maybe 290, 300,000 vehicles. That's at least our target. But for this volume that we have, we still have quite high variants of the vehicles. And since we need to design for each of these vehicles specifically, we need a fast and effective design process for all our components, including electrical machines. That means that we need to cover a wide range of rotor topology in our design process. We need to cover different winding configurations. It can be hairpin, it can be random wound in one motor, depending on the volume. Because as you know, yes, depending on the number of vehicles we produce, we can decide basically if there is a good business case behind the hairpin winding or not, or we should continue, for example, with the random winding. The same with the rotor topology based on the efficiency target we have, the sustainability target that we have, it enforces the kind of rotor topology that we use. So addressing all these requirements with one basically design process, but for different vehicles has so far ended up in a design process that can find a good compromise for each vehicle, but basically between performance, which is our main target because we are an electric performance car, range and efficiency, of course, is super important, sustainability, especially you will hear more about them in future, and also cost. but we are not the cheapest brand in the market. So maybe we can make some compromise on the cost in comparison to performance, efficiency, and sustainability. The design process that we have, you can see it in this basically a slide. I more or less presented this one with a little bit less details last year. So basically, we will start with the system, receiving inputs from our system colleagues, showing us the kind of performance requirements we have on each component, not just in a steady state or like a continuous operation, but also during the duty cycles as well. Then we will do some initial dimensioning of the e-motor, inverter, and transmission to find the best combination of these three components when it comes to the current rating of the inverter, to the size of the motor, and the gear ratio of the transmission system. After that, after initial dimensioning, we go to the component design. And my focus today is on the electrical machine concept design. And that's where we used the built-in process in JMAG, which is based on the genetic algorithm. We make several normally concept designs. We put it on the system studies. We have a tool, we call it internally VSIM, that's basically model the whole propulsion system. And then we will see with that specific motor model, are we able to meet our performance requirement, our range requirement for different vehicle segments under each vehicle program, basically. And then when this is done, our concept is finalized, then we of course go more into the detailed design. That's where we move from parametric optimization towards topology optimization, where we fix all the rotor barriers and etc. for the NVH for the other reason. One very important update that we have made in comparison to the last year is that we are now further integrating mechanical evaluation and also thermal evaluation into our design process. And now for that, we are using, based on the thermal side, we have started to use particle works. I have some slides on that and also a small video showing how we model basically the flow. And as I said, if there is any question, my colleagues who are expert in this software will help you to answer the questions. Yes, and at the end of the day, this is the software that will determine and will enable maximum utilization of the hardware. So that's why you can see the red arrow here. After finalizing the component design, we go for the software optimization, basically to just enable maximum potential of the hardware when it comes to the performance, when it comes to getting the maximum torque in the field weakening region, or maximizing the efficiency at low torque mid-range speed. That's where matters for the vehicles or passenger car vehicles. Here we are talking about maybe 30, 40 Newton meter, maybe 6,000, 7,000 RPM here. Yes, the methodology that we have for optimization of the components is based on a genetic algorithm. This is a built-in function. If you have used JMAG, you should know about it. And in summary, basically, we start from initial dimensioning. We go to making the template. This is an example of a double layer U-shape. We will make the template parameterized in the way that we want. We add parameters, we remove parameters, we go to the optimization process, we find the best design that addresses our need, basically. And then after, this is on the parametric side. And then, as I said, we will use also a genetic algorithm, the same optimization methodology, but this time not for parametric optimization, but more for topology optimization, where we focus on small changes in the rotor barrier toward NVH, improving the efficiency. This is an example of the optimization that we have done. And in this case, we were targeting basically the sustainability, and we were trying to use, instead of copper hairpin, to use aluminum hairpin to improve sustainability aspect of our product. You can find the full report of this study in the paper presented in ICM a couple of weeks ago. And as you can see, this process basically enables us to achieve the level of the performance we want, the level of the efficiency we are looking for, and also the level of the sustainability we are looking for, which here we are talking about ELU, environmental load unit, as a parameter to evaluate the level of sustainability of the product, basically. Yes, but as I mentioned, our optimization is not limited to basically motor itself. So in order to have maximum utilization of our hardware, it is important to have also good software supporting the hardware, both on the vehicle level and also on the component level. And the software for the motor basically means the control. Uh, so when we are finalizing after initial dimensioning, doing concept design, but before finalizing the concept design, normally we involve also some control, basically optimization, where we really take advantages of the very wide selection and freedom that we have in the circuit of JMAG Designer, where we are able to have at least some simple PWM control, where we can change the switching frequency, we can change the DC link voltage, and see its impact on the motor performance and the losses. Of course, this kind of simulation can be time consuming, especially in the first transient. And in order to address this challenge, basically, we are using JMAG RT, where we run the transient part on the analytical based on lookup table RT solution. And then after reaching the steady state, then we will shift from the RT supply to the motor to the inverters basically, and where we see all the switching effects and their impact on the losses and the motor performance. So this is also one operational function that we have in Porta, and we are using it in the right way to optimize the switching frequency, maybe to study the impact of the level of DC link voltage on the motor performance and the system basically power. The other add-on that we have made in comparison to the last year, and it's working pretty fine, but we have still some challenges, and I will mention that, is using particle works basically to do the concept design of the especially direct oil-cooled electrical machine. As you know, when we move from like random winding to the hairpin, we end up in a structure with very small distances between the solid parts. These small distances, if you use conventional CFD simulations, basically it ends up in pretty high resolution, high number of elements around that region, but also it influences the size and the number of elements used in the neighborhood area of that region, basically, especially when it comes to the hairpin winding, as I mentioned before. That is why we decided to move to particle works, which is basically a solution based on the particles, and the element size is basically the particle size, not the shape and the resolution of the solid parts in the structure of the motor. Using this method, we are able to run transient simulations in quite good time. The latest numbers that I had from my colleagues was 3-4 hours for a simulation of 10 seconds for not very small motor, but of course on the cluster together with pretty strong GPU. So we have been able to achieve, and I would say for transient simulation, I will show a video on that, running it in 4 hours. It's pretty good and time efficient, I would say, solution. So this helps us basically to kind of make a concept design on our cooling as well, on the size of the channels, number of channels, the flow of the oil, and etc. This is basically the slide that it was provided by one of my colleagues, basically, and that shows basically our process on doing the flow simulation in particle work. We start with the CAD import, physics setting, inlet settings, and then we need a big post-processing yet in particle work to get the results that we want. And the outcome of this kind of simulation is basically flow distribution and heat transfer coefficient, which are basically the parameters that you need to finalize your concept design. This is a video of the kind of simulation and the kind of solution that I mentioned, that if you have a good GPU, if you have a good cluster, and Corentin has arranged for you a good license configuration, you can run it in 2 to 4 hours, depending on the size of the particles, where you can see how, for example, the two inlets here in this cooling configuration are filling up the ducts, and also then the oil will be collected at the bottom of the machine, and then that's where you have basically the outlet. This is not the cooling system that we are using or we are going to use in future. It was just an example to just show you how you can use this simulation tool to better understand if you have a uniform distribution of the oil, if you have been able to fill up all your actual ducts basically or not, and that's where you do basically the optimization. But when it comes to this software, we have still some challenges, to be very honest with you, that I think in the next versions of this of Particle Works, it will be addressed. And these are mostly on the need for a lot of post-processing to get the results in the level that you want. For example, to get the heat transfer coefficient, you need to run some specific codes to get the data in the format that you want, and you can compare with the other concepts. We are really hoping that this issue will be solved. The other challenge that we have is on the link between JMAG and Particle Works in terms of the CADs, that we think it needs to be improved, because today, basically, there is no direct link or easy link to be used. So there is need for some other software to come in to just export the CAD between these two software. This means that there is no direct link between electromagnetic design and the thermal design. So the CAD and the post-processing of the data are, I would say, the challenges, and there is room for improvement. Thank you very much for your attention. I try to summarize what basically we are using in JMAG, Express, basically JMAG Designer, integrating the control, and also the thermal simulation. I didn't want to go so much in detail, since my colleague Andreas Carlson will have a separate presentation tomorrow on our basically details of our design process, and he will show you more technical picture of what we are doing in Polestar tomorrow. Thank you. If there is any question, I and my colleagues are here to answer.
Thank you, Shafiq, for your nice presentation. Yes, if you have any question, you can ask them with the second mic. Oh, sorry.
Hello, thank you for your nice presentation. Xavier Robin from Hexagon. In the really beginning of your presentation, you show that you have 1, 2, 3 models of car maximum. So I guess behind you have only 1, 2, or 3 types of motors. So the type of simulation and process you have shown, are you doing it continuously with continuous research on new design, new types of motor topology for the future? Or do you do it once for one car and then you stop, and yeah, I mean, it's maybe three months of work, and then you come back 2 years later for a new design? Or is it continuous improvement?
It was a very good question, actually. One thing that I would like to mention was that under each of these vehicles, we have different power positions as well. So you can have low power, or like you don't have really low power, maybe medium power, high power, and like X power, we call it XP, HP, and MP. So under each of these vehicles, there are like 2, 3 different variants of the propulsion system hidden. So this is one thing that makes it quite, how to say, high number of variants. Of course, we do our best to find kind of modularity to reduce this number of variants that is beneficial for our production, for our quality check, for our development cost, everything. But we don't force modularity so much that it will influence our vehicle. So that was one question about the number of variants that we are working on. And about our process, if we do like 3 months, no, it doesn't work like that. So we will start normally from a concept design. The concept design for us takes something like 6, 7 months, basically. And the reason is that because we need to do a lot of iteration on the system level. The component performance and efficiency doesn't have a meaning on the component level. Everything has a meaning on the propulsion system level. What matters at the end, it doesn't matter if you have the most efficient electrical machine, but what matters is to have the most efficient propulsion system. So this iteration normally that we have made from JMAG using speed priority and accuracy priority, we generate the maps for our system simulation. Normally takes time. We need to send different concept to the system simulation. We need to get the feedback. We need to fix it. That's basically the concept design part. After that, we go to the detailed design part. So, and that maybe takes another like 3-4 months. So our design process actually to get to the level that we can have the first or second round of prototyping, it takes something like basically 1 year. And then after that, the vehicle programs we have. So we maybe produce 100 product, then maybe produce 500. These are before getting into the production line. And in each of these, basically a stage of the vehicle program, we try to still modify our prototype or our design until the time they are on production line. So the answer to your question is that our design process and design improvement is continuous. And that's the way we do it, but until they are on the production line. What I can tell you is that also before one product is on the production line, that takes maybe 2-3 years from the time we start designing, we have also the other variants. So the way that we work in Polestar, we always have basically one or two like a mainstream design process that is ongoing by 2-3 maybe engineers on the electromagnetic design, but also we will have in parallel to that, a lot of verification and adjustment of the model, improvement of the design for the other products in the portfolio as well, where we have the prototypes on the bench being tested, being verified, and we are correcting basically our model, and we are further improving our design based on the feedback that we have, not just on the performance and efficiency, but also on the NVH and mechanical parameters as well. I hope I answered your question. Otherwise, please let me know. I tried to make it better clarified.
Thank you, Shafiq. Any other question?
Hello, my name is Bernd Zabulski from IB, Germany. Thank you for the nice presentation. Regarding the availability, cost, and environmentally footprint of rare earth magnets, are there any plans in Polestar or any objectives to use non-permanent magnet machines like induction motors or externally excited synchronous motors?
Yes, we have it for our next generation, because we have a project called Polestar Zero. You can read a lot about it on the net if you just Google it, Polestar Zero. And this is a unique Polestar project aiming for making CO2 level of each vehicle basically to zero. And that's of course exclude the use phase. So it includes from like mining to product based to the vehicle. And then use case, we cannot control so much these days how the energy is supplied when our customers will charge. And also after that end of the use basically. So yes, we are considering that, and you are right. So today that I'm talking to you, permanent magnet machine is not the only motor configuration we are looking at. If I want to summarize, like other OEMs, we are also looking into induction machine, or some people call it ASM, as well as the ESM as well, that you most likely are aware of it as well. So, and as I said, we have under each vehicle, we have different power like positions. So in some configuration, we have 2 motors. In some configuration, maybe we have like 3 motors on the vehicle. And then sometimes we also use combination of different rotor topologies or motor topologies in different positions in one vehicle as well. So we are doing the design, and we are considering different rotor or motor topologies in our design process for our different vehicles and for different power positions in each vehicle as well.
Thank you.
Thank you, Bernd, for the question. Yes.
Yeah, thank you for the presentation. Mustafa Duyar from FEV. So if
Hello,
we
Mustafa.
look at the conventional vehicles with internal combustion engine, so the powertrain and vehicle are developed separately. And once both are ready, then all the business of powertrain vehicle integration starts. So how is the case for Polestar vehicles? Do you start from the beginning interacting with the vehicle team and the powertrain team, and no need for powertrain vehicle integration afterwards?
It was a really good question. Maybe we can also historically say that the first electrical vehicles, basically, or even hybrid vehicle, but more electrical vehicles, were on the platform of combustion engines. But this is something that is changing now. The vehicles are being designed to be electric vehicle in the first place. But to answer your question, that if this is going hand in hand, I can say in Polestar or maybe the other neighboring kind of companies that we work with, we try to get propulsion system design at the very, very early stage of the vehicle. But how is the situation today? I can tell we have room for improvement. So, but this is a very important point because, you know, the vehicle weight has impact on the vehicle performance, no matter of your propulsion system. So if we just do this in series, first the vehicle and then propulsion system, that is gonna make it not maybe the optimum vehicle at the end of the day. This is, I can say, yes, this is something we are doing as much as possible in parallel, but maybe the full process is not yet really in place, and we need to work a little bit harder to make it even more synchronized than today.
Okay, thank you, everyone. I think it will be time to switch to the next presentation. So thank you, Shafiq, for this presentation and your answer to the question. Yeah,
Thank you very much as well, Corentin, and sorry again that I couldn't join. I promise that I will be there physically next year.
Yeah, thank you.
Yeah, and I hope the presentation was clear and the voice and video quality was okay to be understandable.
Yeah, I think everyone was able to understand you. So thank you very much.
Thank you very much and have a good day, everyone.
Have a good day.
Take care.
Bye-bye.
Cheers. Bye. Bye.
Hello, everybody. So now I would like to introduce the next speaker. It will be Bernd Cybulski.